Log on, tune in, find out. Another good idea from Cambridge.
Well, so it's my great pleasure to welcome Dana Testerman from EPFL, who will tell us about nilpotent subalgebras of semisimple algebras, some unexpected torsion.
Right. Okay. All right. So I want to start by giving some history for this problem, even though everyone in the room is in gate theory, but I can still pretend that I'm talking to a general audience and give a little bit of history. In 1961, Borel studied the torsion of the cohomology over Z of a compact connected Lie group. And he called that the torsion of G, okay, so that's what I'm going to call it. And in particular, he studied the relationship between the P torsion of G and abelian subgroups, elementary abelian subgroups, all right? And he showed, among other things, this is Borel, 1961. So I repeat, the P torsion, when I say P torsion of G, I mean the torsion of the cohomology, right? So he showed, among other things, that the fundamental group, connected Lie group, he showed that the fundamental group has P torsion, has no P torsion, if and only if there's no P torsion. If and only if every elementary abelian PP type subgroup lies in a torus. If and only if every, I'm going to write this, PP. So this is elementary abelian, right, to PP subgroup, lies in a torus. Every subgroup lies in a torus. Okay, so that's one thing, right? And so in particular, if this thing has some P torsion, then I can find a PP subgroup that doesn't lie in a torsion, in a torus. That's what interests me afterwards. And more generally, if G has no P torsion, if and only if every PPP, so rank 3 subgroup, lies in a torus. Okay. Now, okay, I'm going to say a little bit more about this afterwards, but he, in his introduction, he laments the fact that he did case-by-case analysis to prove this, and has what I think is kind of an interesting quote, especially because I live in Switzerland now, and I'm Swiss by adoption. He says, yeah, he really puts this quote at the end of the introduction. You have a low shock, keep in mind. We think of things that would never come into a gentleman's head. That's the Swiss national character, dear lady, which I find kind of interesting. So kind of put at the end of his introduction. Anyway, let's see, I was going to tell you something else. Oh, this P torsion, just to mention it. So here. So he showed, not only did he show this, but he also talked about these primes where there would be some P torsion. So he showed that there exists a P. So this is really the case-by-case work, okay? It's to go and find examples, all right? So he showed there exists a PPP not lying in a torus if P is equal to 2 and G is of type En 3, F4 and the E's and G2, and P is equal to 3, and G is F4 1E, and P is equal to 5, P is negative. Okay, so, and there exists, I can't move that one. Can I move that one? No. And there exists a PP not lying in a torus if P divides the order of the kernel of phi, where phi goes from the simply connected group onto 2. Okay? So not only did he give this criteria up here, he also talks about, I mean, he has to come up with some examples, and the examples occur in these cases here. Okay? All right, so in 1975, Steinberg studied the same question, looking at elementary abelian P groups that don't embed into a torus, but for a semisimple, well, a reductive algebraic group defined over an algebraically closed field of a positive characteristic. Okay, and before, and anyway, because he refers to this work of Borel's, he says, I'm going to avoid case-by-case proofs like the plague. And so he gives, he essentially reproves what Borel has already done and some other things, but without ever coming up with these examples here by case-by-case argument. You take a group and look at it and find that example. Now, in order to state his result, I'm going to just, it's not a quote. I didn't want to write all this down slowly because it's stuff that everybody's familiar with, but for the sake of the younger people in the audience, it's on the board now. So if I have a reductive algebraic group, and I have a root system to go with it, and I want to talk about good and bad primes for that root system. If the root system is irreducible, well, say it's irreducible, and I take a base of the root system, and let beta be the unique highest root with respect to that base, and let phi check be the dual root system. So then I'm going to write this highest root as a sum of the roots of the simple roots in the base, and then we know that if you take the co-roots for the roots in the base, that's also a base of the co-root system, so I can write the highest root as an integer being a combination of those. Now p is bad for this root system if p is equal to one of these coefficients, okay? And p is torsion for the root system if p is equal to one of those coefficients.
Okay. Equal or maybe just divide?
It's equal is fine. Yeah. And now, okay, so there's a slight difference here. So p equal to 3 for G2 is bad, and p equal to 3 for G2 is not torsion. Okay, so there's some differences, right? Okay, so that list is still over there. Now, I should say just something else. That's the case where phi is irreducible. If phi is not irreducible, I don't want to write all this down, right? If phi is not irreducible, then you say p is bad for the root system if it's bad for some irreducible component, okay? It's torsion for the root system if it's torsion for some irreducible component, right? It's good for the root system if it's not bad, okay? It's not torsion if it's not torsion. It's easy. All right, and it's very good. That's finally the last thing I want to write down. P is very good for the root system if P is good for the root system and P does not divide L plus 1 when P has type A. Okay? All right, so almost said everything. And finally, I've got a group behind all this. So take G to be a reductive group. Then I'm going to say P is, I'm not going to write all that down. P is good for the group if it's good for the root system. P is bad for the group if it's bad for the root system, etc. But P is torsion or G if either, if P is torsion for the root system that's associated to the group, or P divides the order of the fundamental group. I better decide it. P say that more than any client divides the order of the fundamental group of D. Okay, so I should have written that down before, so sorry about that. What do I mean by the fundamental group? Okay, I can use this. So this G has a maximal torus, and this maximal torus has the group of characters on it. Okay, and these all live in the set, well, the lattice of this thing here is abstract weights with respect to the root system and the fundamental group. Is the quotient. All right. Actually, if you go look in the literature for a definition of this, it's hard to find, actually. and not very consistent. In Steinberg's paper, he actually looks at some dual version of this. But since we're talking about primes dividing this, it's the same thing.
You didn't talk about, I mean, these sort of PP or PPPs, it's all about centralizers being connected or disconnected.
Exactly, yeah. Well, in fact, I'm not going to talk about, I'm not going to actually talk about this because this is all the semi-simple situation, right? So the title has nilpotent in it, but I want to mention it because the answer somehow, what I'm going to tell you in the end, is remarkably similar, even though we're going to pass from semi-simple to nilpotent. So that's why I mention all this. And also, you're getting ahead of me, but I'll tell you anyway. I mean, the question I'm going to talk about is a question that Sarah asked me. And I didn't know where this question came from, but then he explained to me that this question came from exactly this, that somehow it's a general question you can ask PPP subgroups of any type, either semi-simple or not, right? And I think that the fact that the answer ends up looking exactly like the semi-simple situation is interesting, okay? But that's not what I'm going to talk about. Anyway, but Steinberg showed, now that I've said all that, Steinberg,
Underneath the table here. Underneath the one in front of you. Right in front of you.
oh, so what Steinberg showed, well, was essentially the same thing as Burrell, but without a case-by-case proof. So Steinberg, so I just recall here, G is reductive over an algebraically closed field, and P, I want to be a prime different from the characteristic. So that I'm talking about semi-simple elements, okay? Then his first theorem, the following are equivalent. P does not divide this order, now that I've written it down, and say it. So T and force. Okay, maximal force. If P doesn't divide that, then the centralizer of every element of order P is connected. Okay, Q. The centralizer ng of T for every P, T, of T and T, such that T to the P is equal to 1 is connected. So that's what we were saying, right? And 3, every rank 2 subgroup, so every PP subgroup lies in a torus. Every PP subgroup G is contained in a torus. Okay? So that's what Gary was referring to before. This is, okay, it's easy to see why these two things are equivalent, because, I mean, if you know that every element of order P, its centralizer is connected, so then you just put this thing lives in here, okay, and then go find another, take semi-simple elements and here commuting ones and put them inside of a torus in there. Okay? So what's interesting is the fact that when P does divide this, there exist PP subgroups that do not lie in torus. And that's what the interest is. And it's really interesting that he managed to construct those in a general way. And the second theorem deals with precisely those, the rank 3 ones. On theorem 2, following our equivalent. P is not torsion G of every elementary abelian P subgroup. I'm not sure of rank less than or equal to 3 lies in a torus, and which is equivalent to every PPP of any type lies in a subgroup. Lies in a torus. Okay. All right. So that is all history. And so again, the interesting thing, well, okay, the whole thing is interesting maybe, but he constructs PPP groups that do not lie in a torsion for every torsion prime for G. Okay? And in a general construction, with a general construction. All right, now, what am I going to talk about? I don't think this so much about semisimple elements. And anyway, like I said, the question I'm going to talk about is something that Sarah asked me. And then I was lucky enough to have Paul Levy in the office next to mine for a while, and George McNinch visiting from the States for a while. And so this is joint work. So that was all introduction, so not all problems. This is joint with Paul Levy and George McNinch. Okay. Is the following question, given so given G, say a semisimple algebraic group, overall field, algebraic field like before, a characteristic P. Okay, let N be, okay, well, now I'm going to look at elements of order, okay. I'm not going to write this in, I'll just say. So what would be the natural thing to look at next if I'm going to switch to being in the same characteristic, as opposed to looking at semisimple elements, I would be looking at unipotent elements. Okay? So you can ask yourself, if you have some commuting unipotent elements, can you put all of that in, well, what would be the natural place to put it would be into the unipotent radical of a Borel subgroup. Okay? So this is this maximal connected unipotent group. All right? And, okay, so you can ask the question, if you have, even more generally, if you have a unipotent subgroup of such a group, can you always put that inside of a Borel subgroup? And the answer is yes. Okay, so it doesn't have to be connected, it's just a unipotent subgroup. All of its elements are unipotent. Can you put it in a Borel subgroup? Yes. Okay, so it looks like the question has kind of answered, but that's not the question he asked. If you think sort of scheme theoretically, then you could also be talking about unipotent group schemes, and these group schemes might have dimension 0. So then you're talking about restricted subalgebras of your Lie algebra. Right? So then you can ask the question, if you have a subalgebra of your Lie algebra consisting entirely of nilpotent elements, can you put that into the unipotent, the nil radical of a Borel subalgebra? And that's the question he asked. Okay? So this is the question I want to let N be a Lie algebra. A subalgebra consisting of nilpotent elements. Okay, so I don't want to write that every time, so I'll say a nil subalgebra. Okay, the question is, does there exist a Borel subgroup such that N lies in the Borel algebra of the Borel subgroup? If you get it in there, then you get it into the nil radical, because all of the nil radical is the set of nil. Okay? So that's the question. All right? And the answer is not always. And the theorem that I should probably leave this, because I mean at the end I can come back and say the same thing. Oh, I'll leave it. Cover it up. Then the theorem is, if and only if, so the answer to that question is, if and only if P is not a torsion prime for G. So as above and above, then N lies in the algebra of Borel, if and only if P is not torsion for G. Okay? All right. And what we get, in fact, you'll see from the, I'm going to describe the construction. So in fact, we show that if P divides the order of this fundamental proof, then P divides, yeah, then there exist E and F. Okay, this is, I'll give you a, yeah, there exist E and F in the algebra P, both dying at P and commuting. So two P elements, right? So it's like your PP thing, right? Such that the subalgebra that you generate by those two doesn't line up real. So it's exactly analogous to what Steinberg gets, right? And if P is torsion for the root system, which is the other way of being torsion, so that's we get that. And if P is torsion for the root system, then we get a three-dimensional thing. There exists E, X, and Y combining it. P, and all commuting elements. Such that the subalgebra generated by them, or the space band, does not line up real. Okay, so, okay, now I'm gonna, because I have time to do it, I'm gonna describe the construction, all right, and I'm gonna describe the proof, right, in the positive case, in the positive direction. But yeah, I mean, I think the nice thing about it is that we find exactly, for reasons that I don't understand, you know, we find exactly the same sort of setup. Okay. Two-dimensional things for this kind of torsion prime, and three-dimensional things for that kind of torsion prime. Okay.
Are the bad nilpotents somehow the limits of bad semisimples?
Pardon?
Are the bad nilpotents somehow the limits of bad semisimples?
I mean, this somehow should be the philosophy, right? I mean, that's exactly, yeah, that should be the idea, right? The things that you know, yeah. But I don't know, we don't see that. I mean, if that's the end of the question, we don't see
That
that.
makes sense of that, because you're small developments of over 5 or something.
Yeah.
But yeah, I mean, one thinks that if the answer is the same, there should be a connection, but. I mean, I'm going to describe the proof, but like a lot of things, I won't claim that we have the right proof, okay? I mean, and when you have a result that looks nice like that, you sort of wonder what the real reason is, and so, you know, well, between Wilhelm and Steinberg, there was 15 years, so maybe somebody else will find it. Okay, now before I go forward, I wanted to mention one other thing, not to forget to mention. There's Kraft and Kuttler and Dema, I don't know how to say that name actually. They studied something similar, and I don't forget to mention this. So they, instead of looking at nil subalgebras, they looked at subspaces of the Lie algebra consisting entirely of nilpotent elements, and asked what the maximal possible dimension of such a subspace was, right? And then showed that under certain restrictions on the prime, which are kind of similar to ours, that if you have one of maximal possible dimension, then in fact that dimension is the dimension of the nil radical of the Borel, and so it's actually equal to it's a subalgebra, not just a subspace. Okay, so if you're, it's just to say that there's other stuff in the literature on that same problem. Okay, so now, let's see, I can actually, this is a rare pleasure for me to be able to talk about something that fits in 1 hour, and I can really tell you how the proof goes, instead of just vaguely describing it. So, that. Okay, I think I can erase this. Anyway, you got the point, right? It's all happened in Switzerland, this research. And our proof is case by case, and I don't know what that means anyway. So. All right. Okay, now the positive direction, that is, if I keep away from torsion primes, then how do you see that every real subalgebra is contained in a Borel subalgebra, so the positive direction, is not really, I would say, due to us. Essentially, there's enough in the literature to convince yourself of that, so I'll just give you a sketch of how it goes. You have to just be careful about the different primes, but suppose P is not torsion P, okay, and I'll let N be the one algebra. Okay. Well, I want to get rid of some easy cases in the beginning. Let's see. Suppose that G is SL. It's going to be useful to do it first, and then I can use it later. So SLN, right? Then if it's really SLN, then this is no problem, and you're just going to argue by induction. This guy has got to fix something on the natural module. It's got to fix a triviality on some space, and then you continue, and you're going to get a the other triangular real matrices. Okay. All right. So that's how you do SL. Okay. And then you might say, well, suppose I have pi that goes from SL onto my group. Okay. But I precisely avoided primes that would cause a problem because the kernel of this thing here now is not divisible by P, right? This guy is a bijectional Nilpotent, and it's a bijection, induces a bijectional Borel subalgebras. So if I have my thing over here, okay, this nil subalgebra over here, I can lift it back to something, and over here is containing a Borel in my pattern, okay? So I precisely avoided things, right? Okay, now for the other, for SP, well, we just have to take a minute to see that the same argument works, because in SP it's got to also fix something, okay? But this fixed something is an isotropic vector, because everything is isotropic, and you continue, right? In SO you have to think a little bit further, but P is not 2.
P is not 2.
Okay? And so you're going to also get it to fix an isotropic vector and proceed by induction. Okay? So in all of the classical groups, we just have precisely avoided primes that might cause a problem, and it works. Okay? So then the next thing that you might want to worry about is P not torsion. Well, that means that P could be 3 when G is equal to G2. Okay? Because that's not a torsion prime. And, all right, so suppose that G is equal to G2, and P is, well, I'm going to specifically concentrate on this case, because afterwards I'm going to do all the rest of it I want. If G is equal to G2 and P is equal to 3, so not torsion, right? So then I look at my G2 inside of SO7, where I've already shown this to be true, right? So acting on its 7-dimensional module. And so I have my null subalgebra in here, which I can put into a Borel in there, okay? So that means it fixes a non-trivial singular vector on this representation, because I already have it in the Borel subalgebra over here, okay? And then you have to check that the stabilizer of a non-trivial, non-zero singular vector in G2 is a parabolic subgroup. Okay, so that's something you have to know. So now I've got my N, and go to the algebra of a parabolic subgroup by arguing in SO first, okay? And so now this parabolic subgroup, so I can pass to the algebra of P over the algebra of the radical, of the algebra, whatever, right? I can pass to this, and now what is this? A parabolic subgroup in G2? Well, then this is an SL2 now. Okay, so I've got an image of my N inside of an SL2, where I also did the thing to be true, because I did SL first, okay? And so now I lift back the Borel is SL2, and that gives me a Borel of G2 when this thing's on. Okay? So now I've done the classical groups. I've avoided P equals 3 for G2. And so now I'm going to avoid one more thing into the general argument. And that is, I'm going to assume that P is very good for a moment, and that G is simply connected. So now suppose P is very good, and G is simply connected. Okay. Oh, no, I don't want to assume this. I mean, assume P is very good. Then I have this isogeny from G to G simply connected. And because I'm assuming P is very good, this thing is a separable isogeny. I've precisely avoided SL modding out by something that divides, okay? So this is a separable isogeny. And like I said, well, you know, I mean, if I've got something nice like that, then there's a bijection on the rails and things, so I'm just going to assume G is simply connected. Okay, so bijection on the rails. Oh, gosh, nobody wants to correct that. Bijection on the rails, so assume G is simply connected. Okay. Yeah, I think I did it correctly now. Okay, so now I've got P very good and G simply connected. And that's very close to, well, in fact, that's enough to say that I've got G satisfying some what people now call standard hypotheses, so some standard hypotheses, which say that if you form a reductive group for H reductive, they say that H, I think this has to be simply connected. I better do this correctly. Yeah, it's simply connected. The derived subgroup is simply connected. P has to be very good. P has to be no good. Yeah, good for the H. And finally, that there's this non-degenerate H invariant form on the Lie output, so non-degenerate, which doesn't interest me. I'm not going to use it, but anyway, I'll tell you what the hypotheses are. Non-degenerate, invariant, H invariant form on the Lie algebra. So, okay, these things are called standard hypotheses, and I mention this because in this case, there's a nice thing that implies that if you have standard hypotheses for your reductive group, for H reductive, then they also, when you pass to a Levy factor, those are also satisfied. And that's what I'm going to need here. So this implies that the standard hypotheses hold for Levy's centers. Okay, and in this case, Primet was the one who told us the proof. I mean, we asked him the question and he came back and said, well, if you assume this kind of thing, certainly you can get it to be true. Okay. So, and here, what do I do? The argument is sort of the natural thing that I think as soon as you start thinking about it, this is what you would try to do, is you take your nil subalgebra, which is a nilpotent subalgebra, and you take something in the center and you look at its centralizer. Okay, so this is the obvious thing that we don't want to do now. And so it's sort of just curious that it doesn't always work. Anyway, so take N, G, and take X not equal to 0 in the center. Okay, then this N is in the centralizer in the algebra. This X, which under the hypotheses that I have is the algebra of the centralizer. Okay, and under these hypotheses, so under hypotheses that we've set up here, the centralizer lies in a parabolic system. Okay, all right, so now I'm in a good shape because of what I said about Levy's. So I'm going to take my n and I'm going to pass this parabolic to the quotient by the radical. The Levy factor also satisfies the good hypotheses, all right? So I'm going to get the image of n lying in a Borel by induction on the dimension. I'm going to get the nilpotent, the nil subalgebra lying in a Borel of the Levy factor, and then I lift that back to a Borel. Okay? All right.
Same as SL.
Yeah. Now, I think I've almost done everything. If you look at all the cases, what would I have left out? It's got to be not torsion, but it's got to be not very good because I just did very good. So that's going to leave the case where G has a factor that's an AL and P divides up as 1, all right? But P isn't torsion, and so again, I'm going to use the same thing I did for SL. Okay, so I'm going to have this isogeny that maps. I mean, it's not simple, yeah. I mean, I'm going to have an isogeny that I can pull back across, okay? So that's not the whole case. All right, so that's the positive direction for which we shouldn't take credit, and I spent a lot of time telling you about it anyway, but like I said, I can tell you the whole story today, so I want to do it. So now, I should talk about the construction of the examples. So the construction of examples. Okay, so there are two types, as I said before. Let's look at the first type. let's suppose P divides this. The order of the middle group. All right, so I've got my group, and so since P divides this, then I've got a map from G, the simply connected group, onto my G. Okay. And I'm going to work actually in the simply connected group first. Okay, so I'm going to build some subalgebra here that's got some interesting properties, and then I'm going to map it down here, and you're going to see that that works. Okay. Well, I don't want to belabor this point, really. So I'm going to show you how it works in SL2. And then you're going to believe that that there's a list of elements that this or subalgebras that behave the same way. And then I'll give you a more, here there is a slightly more general construction. So let's look at SL2. Okay? And so I'm going to map this onto PGL2. Okay, so that's the one here. Okay, well, there's a really strange thing, right? If you take your favorite elements here, so like that, all right, what happens when you take the commutator of them? Well, you get the identity, which is in the center of your Lie algebra, all right? Now, what is the Lie algebra of PGL2? It's the Lie algebra of SL2 run out by the scalar matrices, all right? So when I take this three-dimensional subalgebra and I map it over to the Lie algebra of PGL2, it becomes a nil subalgebra, right? And it is, okay, now, okay, so I'll write that down in a minute. Why does it not have the prayer of being an Algebraic subgroup? Because it's not an Algebraic subgroup up here, okay? And this thing, even though it's no longer a separable isogeny, still induces a bijection on the set of Algebraic subgroups. So this thing here, still, it has central kernel, I mean the differential, has central kernel, okay? And this thing still uses a bijection on the Borel subgroups, right? So now this guy, of course, is not an Borel subgroup because I have two nilpotent elements and I take their commutator and I get something semi-simple, so it can't be, right? If it was an Borel, this part would be in the nil, or in the nil radical of Borel, okay? So it's clear that this is not an Borel subalgebra, and so when it maps over, this image is not either. Okay? So anyway, you can believe now that you can concoct the same kind of examples. All right? You have to look for elements. Yeah. Now, I don't know. I can tell you. I mean, if you were in SL generally, you have to take something like that, and then to make sure that you get the center, you compensate with something like that, which is SL2. Okay? And if you have SL big, or P divides big, all right, and you can just put a bunch of blocks like this down the diagonal. Okay, so you can take, so and the commutator is going to be the identity. Okay, and then in the other groups, well, you have to go. In each case, we have an example, right? And we find elements with precisely this property, and E and F, so that their commutator is the center, in the center of the algebra. Okay. Now, if you that's sort of unpleasant. Let me tell you a slightly more general argument. These, we were looking for small examples in the sense that we thought it would be nice if these subalgebras were restricted subalgebras killed by P already. Okay? And so, in fact, that's the case we find in every case, as I said before, P after the P is equal to 0. But if you don't care about that, and you just want to find a subalgebra with this property, here's a more general argument. You could take E to be regular, so a more general construction. For this case, you could take E to be a regular nilpotent. Okay, and then you can associate to it a co-character, even if the prime is bad. It's got the property. Well, they put the grading onto you. Okay, so that tau. Associated to E in the sense that, well, all I need in this case is that if I take tau of C and I apply it to E, then I get C squared. So E is weight 2 for this character. Anyway, this puts some grading under the algebra, and it's still the case even in bad characteristics that add E sends the -2 part bijectively onto the 0 part. So this is a bijection. Okay. In any case, it always add E is going to move you from one space, weight space, to the next weight space plus 2 because of that. And anyway, this is bijection. It's regular. Okay. So now we are precisely in a situation where the Lie algebra of G has some center, right? And the center is a semi. It's in this 0 weight space here. Okay. So I can find something in the -2 that maps onto that central element, right? So there exists. Okay. So let W and here intersect the center of the Lie algebra. Okay. And then there's going to be an F that exists in F and here, such that EF is equal to W. Okay. This is probably messed up here because I should have put simply connected. Yeah, I'm doing all this in the simply connected group. And, okay, so now I've got exactly the setup that I had before. I've got these two nilpotent elements, which won't be killed by P in general now. All right, you'll have to have a higher power P to kill them. But anyway, these two nilpotent elements that commute modulo the center. So then I map them over to the group modulo the center, or whatever part of the center I need to map out, and I've got this dimension. Okay? So that's one construction, and which is absolutely clearly linked to having a kernel in this, having P divide the kernel of the covering order. Okay. Now, the other examples, I can't, we don't have a conceptual way like that of seeing them at all. So, just say, after I'm going to give you one example, and then say some words about what the fact that they all have something in common. But we don't really understand very well. Okay, so the second construction. So this time, I want to say that P, assume P is torsion for the root system. Okay, so I've already dealt with, this is exactly the situation where P is torsion in the other sense. Okay, and so now I take it to be torsion for the root system. All right, and what is it I said I wanted to find? I'm going to find three-dimensional subalgebras this time. Subalgebras, okay? And, well, I'm going to find it in G simple, and if I can find such a subalgebra in the simple factor, then I'm not going to get that subalgebra lying in the middle of the whole thing. Okay, so it's not to look at the simple. And I'm just going to give you an example in D4 when P is equal to 2. Okay. And unfortunately, I'm going to write down elements. And then I'll just say some things about the other examples. Okay, so I'm going to set E to be, let's call these things something. 1, 2, 4. Okay. Take E to be E of 1 plus E3 plus 4. So those are the root vectors with respect to those roots. Okay. Take F, no, I'm going to call it F because that was the wrong idea. So take X to be E alpha 1 plus alpha 2 plus E alpha 2 plus alpha 3 plus E alpha 2 plus alpha 4. So the sum of all the roots of height 2. And take Y to be E minus alpha 1 minus alpha 2 minus alpha 3 plus E minus alpha 1 minus alpha 4 minus alpha 2 minus alpha 3 minus alpha 4. So all the roots of height 3, but they're remainders. Okay, all right. So now, well, okay, you sit down and you check, and you see that these elements commute, all right? So they generate a three-dimensional subalgebra. They're all just sort of A1, A1, A1 type elements that are all killed by P, all right? And, all right, so I've got a three-dimensional commutative subalgebra. And the question is, why can't this thing lie and a Borel subalgebra, and that's just a root system sort of thing. I should really give Paul all of the credit for this part because he's the one who saw how to construct the first examples, and then there was a machine turning. We had some idea where to find it, but anyway. Let's see. So how do we see that this thing doesn't? So that n be the span of these guys. Okay. So how am I going to convince you that n doesn't lie in a Borel subalgebra? So I've already clearly written this with respect to a fixed choice of base. Okay. So if I can get it in a Borel, I should be able to use the decomposition. There exists, suppose. There exists a U1 and a U2, and the radical of B, and an N is an analyzer of P, such that U1 and U2 acting on the subalgebra lies in the algebra of B. Okay, so suppose you have that, right? Well, look at your element E. So, well, okay, I can forget about this lies in the subalgebra B, so I can forget about this U1 over here, right? Because I can shit about that. And so now I'm looking at N U2, applied to, well, E subalgebra, right? Okay, so this, I mean, the elements have a particular form. So if you take something in the input round called a Borel and you apply it to that thing, you're going to get E back, of course, and then you're going to get a sum of some root vectors of height bigger at least 2, right? Plus X, where X is in the span of some root vectors of height at least 2, okay? And then you're going to come along with this N, this N applied to that, sorry. And then you're going to come along with this N, and well, N is going to see here, okay, anyway, there's no cancellation, that's the point. N is going to see alpha 1, the alpha 1, so N is going to send alpha 1 into the positive roots, okay? All right, well, you argue similarly, it's got to send alpha 1 plus alpha 2 into the positive roots, okay? And it's got to send minus alpha 1, it's got to send alpha 2 plus alpha 3 into the positive roots, that's what I meant to say. That's got to send argument, but it's also got to send minus alpha 1, minus alpha 2, minus 3 into the positive roots, and well, that's just not possible, okay? So each one of these elements, in fact, is conjugate to the first one. It has got the same kind of configuration of roots, okay? And you can't, so I'll just finish the sentence here. Similarly, N has to send alpha 2 plus alpha 3 into P plus, and minus alpha 1 minus alpha 2 minus alpha 3 into P plus, and that's of course not possible. Okay? All right. Now, all right, so let me just make some comments about the examples. They're all like that. I mean, all examples are an E and X and a Y where there's some root system thing like that going on. Okay, so everyone is like that. So the proof, once you've written it down, is general. Okay, there's always some root showing up so that the sum is equal to 0. Okay, and okay, so. And also, one more comment, I mean, once you've done D4 like this with P equals 2, you've also done the E's or anything, the simply laced ones, because this example will work for all of the E's, okay? And the same thing if you want to find an example for a B, okay, when P is equal to 2, right? Then you can find a small example, and then it happens in all of them, okay? So we don't have to do a general thing like that. All right. Now, once you have these subalgebras, you sort of think that there should be some rhyme and reason to it all. And one of the questions okay, before I say that, let me say something else. What is funny about these examples? I mean, why do they exist? Well, essentially, the problem here is that if P is good, then you expect the Lie algebra centralizer of an element, a nilpotent element, to lie in the positive part with respect to this co-character. So there is still going to be, like, that's the thing to point out. This element is not a weird element. It's not something that exists only when P is equal. It's not a new class. It's not because it's splitting of classes or something. It's a perfectly nice element, right? And it's true in all of the cases. The elements they're not some new class of nilpotent elements, okay, that arises only in small time. But the difference is that, and you can write down a co-character for this thing, which has the same nice properties, some of the same nice properties, in the sense that this guy, like Garrett was talking about yesterday, this guy is distinguished in an A1, 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 okay? And you can write down a co-character, his one-dimensional torus, whose image is in that A1, 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 which has weight 2 on this element. Okay, so this you can write down. This is all okay, right? The funny thing is that with respect to that co-character, you get -1 stuff in the centralizer. Well, some negative stuff in the centralizer, and that's what usually doesn't happen, okay? And in all of our examples, all right, what happens precisely is that this spans exactly the -1 stuff in the centralizer, okay? And that enables you to see that the normalizer, this was a question that Sarah asked after he saw the examples, well, what's the normalizer of this thing? What can you do to this subalgebra? And the normalizer of this in the group is an SL3. And you can really move these guys around. These elements are all conjugate, okay, which is visible here. And you can move around inside of this normalizer modular centralizer is an SL3. Okay. And I think that's all I want to say. I've said all the normalizer. And yeah, that's absolutely all I want to say.
Any questions?
I have a question and a comment, okay?
Yes.
So the question is sort of about conjugacy of all sorts of things like that.
Yeah.
You sort of can do that with a semi-simple case.
Yeah, exactly.
Okay, is there an answer there?
No, we don't know, but that was the referee said, well, now you should try to classify these guys. Right? And you should try to understand their existence. And that's, yeah, it's something to be done. I have to say that I have never in my life tried to write such a short paper. So the whole game was keeping it under 6 pages.
No, that's it.
Yeah, it's another question, right? Yeah, we don't know.
The comment is, this is sort of relevant to Ron's question, was, so let's go back to the SL2. If you go to the SL2, the smallest example, the way you would find a semi-simple version is to just take the quaternion group sitting inside of an SL2, where the elements are all of order 4 and regular semi-simple. So you're sort of doing the same thing, but you're replacing regular, nilpotent by regular semi-simple.
Well, I mean, somehow this limiting idea is something that I've thought a lot about lately. I mean, how much information can you obtain about unipotent elements or nilpotent elements by seeing them as limits of semi-simple, right? And okay, there's the sort of classic argument that that's how you get that there's always something abelian of dimension at least equal to the rank in the centralizer of the element. But you could specialize precisely. You could say, okay, I don't want to do it generally. I'm not going to just view it as the limit of any old thing, but try to pick some semi-simple elements naturally lead to your, but I mean, in a different context, I've tried to force that to show something, and I haven't gotten, so I don't know in this context.
What was Steinberg's construction?
He actually generally he has some element, and then he goes in the vial group and finds some elements that act correctly. I mean, commutators and stuff like this. But I mean, he generally starts with an element of order P, and then goes to look at looks inside of a, yeah?
You can just generalize the same thing. You can take for SLP, you can take which is am I getting it right? Yeah, you take an element of order P and another one, and they extra special.
Yeah, but for the other ones, but for the PPP, what he does.
For PPP.
For the PPP, yeah. I mean, the 2 ones are kind of similar, but the PPP ones, I think, my recollection is that he's actually looking for elements in the vial where he has some limits which do certain things. But in a general way. So, I mean, this has certainly led me to want to read that paper carefully and understand it.
Any other questions? Yes. So let's thank the speaker again.